Okay.
Let's begin. Consider, one of the scariest words in mathematics, consider this integral. Is that the one I want you to consider? Yes, it is. Consider that integral. How would you attack that integral based on what we've seen so far? Here's one way to attack this. We could actually complete the square here. What would completing the square look like in the denominator? Yeah?
2.5.
Come again?
X minus 2.5.
5 over 2 squared. So if you square this, you get a plus 25 over 4. How do you get to a 6?
18.
Huh? What?
Minus 25.
Come again?
Minus
1 over 25.
Minus 1 over 25?
No. Minus a quarter.
Because 25 over 4, you need 26. It's 1 over 4, right? Okay, so you could do that, and then you could apply a trig sub. And what would the correct trig sub be?
Secant, x equals 1/2 secant theta.
No.
Actually, x minus 5 times.
X minus 5 over 2 is equal to 1/2 secant theta. And after this, it's like, yeah, nah, you're not going to do that, right? It's kind of getting annoying already. You're going to be doing a trig substitution, all these fractions. Doable, don't want to do it. Here's another way. One thing we could do is to realize that this integral here is actually equal to this integral over here. Right? And you can check if I add these two fractions over here, it'll actually combine and give me that fraction over there. Because we go x minus 2 minus x plus 3, that gives me a plus 1, and then multiplying these across will actually give me the denominator. Now each of these you can integrate easily. X minus 3 ln of x minus 2, and that's your answer. So everyone's got it? Good. Right. That's pretty much all for this section. That's not all for this section. Like, how did I know that? Like, how did I know how to do that? You just looked up the example before coming to class. Like how did we do that? Is going to be the question of the day. When can we do this? How do I know that would work as opposed to trying something else that might be more annoying? See, here's some vocabulary here. When you have 1 over x squared minus 5x plus 6, and you can break it up into smaller fractions, namely these two. These guys over here, these guys are called the partial fractions of the guy over there, right? And as you can see from this example, the idea behind even needing to do this is that the integral of a big fraction is going to be equal to the integral of its smaller partial fractions. And of course, the upshot is this is easier to compute. I mean, looking at this guy directly, if I wanted to do that without breaking it up, I would have to force myself through a really messy trig substitution, and which is doable, but you don't want to waste time doing that if you can avoid it. And it turns out this provides another option that in many ways can be quicker, although in many ways it won't be. But it will work potentially in situations where a trig substitution won't work. It will also just be a nicer way to approach things. If only there was a way to go from the bigger fraction to the smaller fractions. Yes, there is. Okay, so that's the title of today's class. We're going to learn about these guys. We're going to talk about partial fractions. That's 7.3 in your textbook if you're keeping track. Partial fractions. Decomposition. So when you break a big fraction up into little smaller fractions so that when you add up all those small fractions you get the big fractions, you say you've done a partial fraction decomposition. That's the name of the process. So this process here is partial fraction decomposition. Of course, the idea being dealing with the smaller fraction is going to be easier than dealing with the bigger fraction, especially in a calculus context like finding an integral. So how do we actually go about doing this? Well, that's going to be the first thing. And then we're going to put it all together and actually do some integrals using this technique called the technique of partial fractions. So how do we do this? Well, there's a sequence of steps. Step 1. So you're looking at something where potentially there's going to be some option of breaking up a big fraction into smaller fractions. And again, once we start piling on more techniques, I'm going to tell you how to choose when to do which. Why would I choose a trig substitution over a partial fractions, over a regular substitution, or something else, right? So step 1. So first, note this technique only works with rational functions. That means you have one polynomial divided by another. So that's one situation in which you wouldn't want to do a partial fraction, is if you don't have this. So if you had this, you had the option of doing a trig sub or breaking it up like that. If you have this, now you need to do the trig sub, right? Because it's not a rational function. So it has to be a rational function, so a ratio of polynomials to even think about doing this technique, so that's the first thing. But more importantly, it has to work on a special kind of rational function. And the function must be proper, i.e., the degree of the top, the degree of the numerator must be smaller than the degree of the denominator. Right? So step 1 is to say, if not, make it so. Just like, I decree that this must be, make it so. Now, how would you make it so? Well, there are two main ways. One, you could just do some algebraic manipulation, which I'm going to show you some examples of doing that. Just some clever tricks, multiplying and dividing by the same thing, or just trying to factor out something to get a clever cancellation to work. Or 2, long division of polynomials. So something you probably covered in pre-calc. It's been a while. We'll actually review that. This is equivalent to another method, although it's better than the other method, called synthetic division, which some of you might know. So that's actually step 1. So the first thing to even start this process, you need to have a certain situation unfolding. You have to have a rational function where the degree of the numerator is smaller than the degree of the denominator. Like in this case, the degree of the numerator is 0. That's a constant on top, that's a 0-degree polynomial, and there's a second-degree polynomial at the bottom. So this was in a good condition to apply partial fractions. Now, so let's actually get through step 1. Let's look at an example. Partial fractions of, let's say I had x squared plus 1 over x squared plus 2 or whatever. So here, you'll notice that this is not proper. So if you were given that, you would have to somehow try to reduce it, write this as a way where the numerator is going to be smaller degree than the denominator. One way to actually do this is to do a common manipulation. So this is a technique that you can try sometimes, and it's try to get the denominator in the numerator. Now, what do I mean by that? Notice here that your denominator is x squared plus 2. Your numerator is x squared plus 1. So what you can do is, the denominator is x squared plus 2. What you want to somehow do is get an x squared plus 2 in the numerator. And oftentimes you can start by just putting it there. So I'm going to put that x plus 2 there. But you can't just randomly put something. You have to make sure that what you changed it to was equivalent to what was there before. So if I have an x plus 1 and I want to get an x plus 2, how do I fix it so that that was legal? So try 1. What I will do is I can rewrite x squared plus 1 as x squared plus 2 minus something, right? So I kind of get the denominator in the numerator. Now, what that will allow you to do?
Divide it.
Yeah, now you divide it, you just split them up.
Leave a 1.
You can split the fractions up. Now you end up in a situation where this is just 1, so this, you reduced it, minus x squared plus 2. Now this here is going to be easier to work with. In fact, if I had to integrate this, I wouldn't even need any further techniques from here, because that's you should be able to see that that's an arctangent integral, pretty much immediate. But I go from a bigger fraction where it's not proper, I can use this manipulation. One way to do that is to force the denominator to be in the numerator, make any changes that you have to make to not change the value of what you're working with, and it'll automatically break itself up into smaller parts where you might have to do more work on this part over here, but then again, you might not have to do more work on that part over there. So this is the algebraic manipulation kind of thing. So that's a common manipulation you can try to do. Try to force the denominator into the numerator, split it, and you can cancel the denominator. So that would be one way. Or, let's look at the same guy. Or, try long division. Mini review. Suppose you wanted to divide 27 by 2. How do you actually do it with long division? Well, you go into the first guy, try to divide this into the first guy. Remind you guys how to divide. You say 2 into 2 goes 1 time, you put the 1 up here. Then what you do is you take that 1, you multiply this 2, and then you put the result underneath that. So you take this, multiply, and then the result goes over here. So you put that 2 underneath here, and what you do is you actually subtract it from the guy above. Now, if I take 2 minus 2, you'll realize that 0 is left. What you're going to do now is you bring down the other guy, and you repeat the process. Now you're gonna say 2 into 7 goes how many times?
3.
3 times. You're gonna take the 3 times the 2, we get 6. We put that 6 underneath this, subtract it, right? Now 7 minus 6 is 1, right? Now 2 into 1, you say you can't, right? So at this point, it's smaller than the divisor. So you stop. Okay? This guy is what we call the remainder. This is the remainder. Quote unquote. And so how your answer would look is if I take 27 and divide by 2, that will give me 13, which is the number up here. That guy is called the quotient. Plus 1 over 2. This is the remainder over the divisor. Right? So in other words, 27 over 2 is 13 and a half. Right? Now, of course, we could probably be able to do that much quicker in your head, but I wanted to remind you of how the process of long division works. You take these guys into the first guy one at a time, keep subtracting them, multiply, put the result here, subtract, bring down the other guy, divide into that, get the quotient, multiply, put it over here, subtract, bring down the other guy, and you kind of just do this algorithm until you get to a point where the thing that you're looking at is smaller than the thing you want to divide into it. And at that point, the result is the remainder, is the quotient up here, plus this divided by that guy. So how would this apply to this? You can do the same thing with polynomials. So if you wanted to do x squared plus 2 over x squared plus 1, what I believe it is. So what you can do is you can actually set up that thing here. So here you'll have your x squared plus 1, that's your divisor, and your x squared plus 2 you're going to put under here. Now there are certain nuances here. You want to account for all powers.
Where you flipped it?
It's x plus 1.
Yeah.
Oh, I had it the other way?
Yeah.
Doesn't matter. So it was 2 down here
Yes. Yes.
and a plus 1 up there.
Yes.
Which means it's a 2 down here and a plus 1 up there. Now, it's still important that when you're putting the guy underneath the bar, you have to account for all powers. So even though there's no x, you need a placeholder for the x, because you're going to want things to line up correctly. Right? So there's going to be this line, this vertical line of things. So you want everything to line up correctly, so you must account for all lower powers. And you're lining this up. So start at highest power and account for all lower powers. So you want to just line up, so it's going to be an x squared, an x, and a constant. So just, even though the constant doesn't show up, you need to put them there because things need to line up properly. That's the first thing. Now, here's how you actually do the division. You are going to take the first guy here, and you're always going to start out with the first guy. Again, here you're going to line up highest to lowest power. Then you're going to take the first guy here and divide into the first guy there. So you're going to take x squared into x squared. That goes 1 time. You're going to take that 1, you're going to multiply everybody here. 1 times this, well, that's x squared. 1 times a 2, well, I'm going to make sure to line that up over here. And then we're going to subtract this line from the line above. The x squares die. There are no x's, and now I have 1 minus 2. Realize now there's a minus 1 remainder. Now, my x squared cannot go into the minus 1, so at this point we stop. Because there's no x, I need at least an x squared here. Here I have an x to the 0, I can't actually divide that into it, so that's the remainder. So at this point the answer would be the following. 5x squared plus 1 over x squared plus 2. This is going to be the quotient, right? You take the top guy, you write that down, that's 1, plus you're going to take the remainder and put it over the divisor. So I'm going to take this minus 1 and put it over this guy. In other words, this is 1 minus 1 over x squared plus 2. And you'll notice that that's what we got last time, right? So here it took you a lot longer. But again, this process you can get really quick with it, as well as the algebraic manipulation way doesn't always work, or it's not always so easy to see. So that would be longer. Don't want to spend too much time on that, so I'll just do like one example. We'll do many more examples where you have to do this. But any questions on this? Yeah.
So for the answer, you said that 1 over x squared plus 2 is arctan. Isn't it 1 over x squared plus 1? Isn't that what arctan is?
Yeah, but I can factor off the 2. You're talking about the integral?
Yeah, talking about the, yeah.
Yeah, I would factor off the 2. And this would be x over radical 2 all squared plus 1 dx, and do a u substitution for x over radical 2.
Alright.
And so this is going to be, well, 1 over, well, radical 2 over 2 of 1 over u squared plus 1 du. And that's the arctan. Yeah. It's a constant. You can always factor constants up. So, yeah. But for now, I don't want you to worry about the integration too much, just the manipulation of actually breaking this thing up. So in terms of the long division, you get that. Okay, so that's step 1. So step 1 is the first thing you want to make sure is the highest power in the numerator is smaller than the highest power in the denominator. If it is not, you're either going to do a long division, or you try to manipulate it some way that you can actually reduce things a little bit. And this brings up to step 2. I want to factor the denominator completely. That's step 2. Now, I'm going to assume you all know how to factor. I'm going to teach you how to factor again. Step 3. So step 1, make sure it's a proper fraction. If it's not, reduce it with long division or algebraic manipulation. Step 2, factor the denominator completely. Whatever happens, whatever you need to do that, just do it, get it done. Now step 3, you're going to break the fraction up into pieces. Where each factor from above is its own denominator. And the numerator of these fractions will be generic polynomials of specifically 1 degree less than the factor of the denominator. Now, that's a mouthful. Let me show you some examples. If I do a bunch of examples, it should be clear what the heck am I talking about. Okay, so let's say you have a fraction. Let's make the numerator 1 just because it's easy. The numerator doesn't really matter. But it factors into x plus 1 and x plus 2. What you do is you break this up so that each of those factors is its own denominator. X plus 1, x plus 2. Now, in the numerator, what you're going to do is you're going to create some generic polynomials that are specifically 1 degree less than the denominator. So if you look at the denominator, this is a first degree polynomial. It's a line, which means on top, I need a 0th degree polynomial, which is a constant. I just need a generic one, so I'm just going to put a letter, A. A represents some constants, it's a 0 degree polynomial. Similarly here, this is a 1st degree polynomial on the bottom, I need a 0 degree polynomial on the top, call it B. So I can take this fraction and break it up into those fractions based on the factors in the denominator. If I had something like 1 over x squared plus 1 times x plus 2, that again is a fully factored thing because you can't factor the sum of squares because we don't have complex analysis. So you would break this up into 2 parts, x squared plus 1, x plus 2. And what you would do is in each numerator you put a generic polynomial of 1 degree less. The denominator here is a 2nd degree polynomial, which means on top you need a 1st degree polynomial, a generic one, ax plus b. Plus, move on to the second one. Well, that's a linear polynomial. 1st degree, which means on top I need a 0 degree, c. So that one would break up. If I did an example 1 over I think you're getting the point, but let me just show you what it would look like for something bigger. You can break it up however many times you need to. So let's say it was x, and then there was an x squared plus 1, and then there was an x cubed plus 7, which is not going to factor very nicely, right? Because 7 is not a nice cube. Then the denominators would be x squared plus 1, and x cubed plus 7. On top of the x, you're going to put an a, because 1st degree needs a 0 degree on top. On top of this, you're going to put a bx plus c, because there's a 2nd degree on the denominator, I need a 1st degree on the top. For the next one, 3rd degree on the bottom, which means I need a 2nd degree on top. Are we getting the idea? So you're going to factor the denominator. Once it's fully factored, you're going to break it into little fractions based on the factors of the denominator. The generic numerator that you're going to take on must be 1 degree less than the denominator, specifically 1 degree less. Right? Step 3b. So there is somewhat of a caveat here. So a secondary requirement in step 3 is for repeated factors. You must break them up further. Counting up to the multiplicity. Let me explain what that means. Let's say you have something like 1 over x plus 1 squared times x plus 2. So here there are really 2 factors. There's the x plus 1, there's the x plus 2. However, the factor x plus 1 is repeated. There are 2 of them being multiplied, right? It's x plus 1 and x plus 1. What you have to do is you have to actually break up the x plus 1 into 2 parts, where you start at 1 and you count up to the multiplicity 2. Now, the numerator still looks at the factor itself. So it's a square here, but we look at the inside. The inner factor is linear, so this is still going to be A, this is going to be B, that's going to be C. If I were to do something like, if when I factored I got x plus 1 cubed times x plus 2, then I would break that up into A over x plus 1 plus B over x plus 1 squared plus C over x plus 1 cubed plus D over x plus 2. If I wanted to, let's say we have this. Just giving you a lot of variety here so you can hopefully you get the answer by the idea by just seeing a bunch of examples. Again, numerator doesn't really matter here because we're assuming it's smaller than the denominator. Let's say I had 1, I had an x plus 1 cubed, and I had an x squared plus 1 squared. Right? You factor it, you get that, right? You would break this up into x, then an x plus 1, then an x plus 1 squared, then an x plus 1 cubed, then an x squared plus 1, then an x squared plus 1 squared. And looking at the inner factors, first degree needs a 0 degree on top, first degree needs a 0 degree on top, first degree needs a 0 degree on top. Again, I'm focusing on the x plus 1, the inner factor, not the square part. So all of these here will need a 0 degree on top. Once I get to this factor, well, that's a quadratic factor, right? The elementary factor is a quadratic. So that's going to need a linear, ex plus f. Same thing with this, g h. And that's how that one will break up. Yeah.
Does the letters matter? Like, could you use the same letter, or you're not allowed to use the same letter?
Oh, you mean like use an A and an A?
Yeah.
No, you assume they're different.
Okay.
Because they're remember, you don't know what the answer is. You don't know that the numerators have to be the same. I just need A, B, and C, D, E, and F, G, and H to work together so that if I were to add all these together, somehow with those tops, they're going to add up to 1 at the end.
Okay.
I'm going to tell you how to figure out what A, B, and C, D
Okay.
need to be in order to make that happen.
Okay.
But in the beginning, you can't assume that, oh, they all have to be the same number. You can't. You don't know. Other questions so far? Yeah.
Why do you only pay attention to the inside factor? Like, why do you just negate the x plus 1 to the
That's a
second
good question. Let's look at it. Let's see why. Why would we do this? And let's say we had 1 over x plus 1 cubed. Okay? So basically what this is, it's that you're trying to apply step 3, but you actually want to break it down even further. It's possible to go even further. So if I were to ignore this idea, the counting up to multiplicity thing, and I saw that the denominator here is technically a cubic, right? Which means the numerator needs to be a quadratic. Now, in order to get things to work out nicely and factor and cancel and do things like that, what you would do is you would think of the variable as x plus 1 instead of just x. And so if you break this up as a quadratic on top, x plus 1 cubed, what's going to happen is on top you would think of this as a x plus 1 squared plus b x plus 1 plus c, right? You'd write out the quadratic in that form, just to make the variables work nice with the denominator, because you're hoping that stuff is going to cancel and things like that. So you just rewrite it like that. Now if you were to break this up, into individual fractions, they're all cubes. X plus 1 cubed. What's going to happen? You're going to realize that this is going to cancel that. You're just going to be left with a over the first factor. This is going to cancel 2 of those. You're going to be left with b over the factor to the next multiplicity. Then you're going to end up with c over x plus 1 cubed. Right? So that's why you only have to worry about the inner factor. Technically, we didn't start out that way, but it actually just breaks down that way, that you only have to care about the inner factor. So that's how we kind of set it up, right? So we kind of take 3 part A, but it logically breaks down so that when you have a repeated factor, we can go even further by doing this clever little trick of changing our variable from x to whatever the factor happens to be. It just makes things work out nicer at the end of the day. So that's why if you have a repeated factor, just worry about the inside and then just count up to the multiplicity. It'll actually break things down even smaller, right? Dealing with these is going to be nicer than dealing with that. Yeah, so that's done. Now, so hopefully we're following so far, because we're going to have to put all of this together all at once, right? So just want to make sure each individual step you understand very well, so that when you have to put them all together, you know what you're doing. Okay, so after that, so you start out with a big fraction, make sure it's proper. If it's not proper, algebraically manipulate it or do long division to make it proper. Then, once you have a fraction where the numerator actually has a lower degree than the denominator, factor the denominator and break it up as described previously. Now, step 4. The variables A, B, C, D, etc. are called, just like with integration, they're called arbitrary constants. Now the goal is you need to find them sometimes. So I believe on the quiz I asked you to break things up into partial fractions, and I had the instruction you don't need to find the arbitrary constants. That means I just wanted you to write the answer in this form, don't worry about what the A, B, C, D's were. But we sometimes need to find them, right? So how do you go about finding the right variables that's going to make this all work out? How do you know this is even possible? Well, there are two main methods. I'm going to talk about separately, but they may be mixed and matched. So you can use both or one of them if you want. But let me deal with them separately. Method 1. They both kind of start out the same way, right? With the given, not given, equation, multiply both sides by the denominator on the left. That's step 1, right? So you have something like this, what you're going to do is you're going to take this guy here, multiply both sides by it. It will clear all denominators because it's going to completely wipe this guy out, but then it's going to wipe out specific factors over here, and you're going to be left over with something else. You'll get equation with no fractions. 2, you're going to plug in convenient values of x. To eliminate as many variables as possible. Hopefully leaving one that you can solve for. Repeat. And it's worth mentioning here, you may get several equations you have to solve simultaneously. Okay, so here's an example. Let's bring it back to the first guy that we were looking at. We had this. How do I know it could break up the way I said it would break up? Well, it's proper. So what I can do is I would first factor the denominator. And that factors into what? X minus 3, x minus 2. Okay. So now what I'm going to do is I'm going to take 1 over x minus 3, x minus 2. I'm going to break it up according to the instructions above. Now I don't know what these constants are going to be, so I write a and b. The next thing I'm going to do is I'm going to multiply both sides by the denominator over here. That's going to result in, right, so I'm going to take this entire equation and I'm going to multiply by x minus 3 times x minus 2. On this side, this cancels that entire denominator. On the right side, the x minus 3's are going to cancel, and I'll be left over with the x minus 2. For this term, the x minus 2's are going to cancel, and I'm going to be left over with the x minus 3. Now I have an equation where there are no fractions. What I am going to do now is, this is an equation that should hold for every value of x. So what I can do, plug in some convenient values of x. What does convenient mean? Variables that will eliminate as many other variables as possible. So, for example, can you think of an x value that I can plug in here that will eliminate,
3.
3. I can say x equals 3. I'm just going to plug that in. Plug x equals 3 to this equation. What's going to happen? I'm going to have a 1, a times 3 minus 2 plus b times, of course, 3 minus 3. That's going to go off to 0. The b is now eliminated. I now have an equation where only the a is there. In fact, I get right away, a must be 1. What do I do now? Repeat. So I'm going to go back to the original equation. Or you can even just write below it. You don't have to recopy the equation. You can just say, okay, now I'm going to plug in x equals 2 would be a nice thing to plug in. Why? Because that will allow me to eliminate the a and get the b. So I can have 1 equals a to the 2 minus 2 plus b to the 2 minus 3. That's, of course, going to go off to 0. I now have an equation with only b in it. This is 1 equals minus b, or in other words, b equals minus 1. Therefore, I am able to conclude that 1 over x minus 3 times x minus 2 is actually equal to my a is 1 and my b, which is over this one, is minus 1. And that's where the fractions that I had in the beginning came from. Yeah?
Can't you just but you got a equals 1, can't you just put 1 back there, solve like
You
that?
could put 1 back here,
And then solve
and
for
you'd
b.
still plug in another value for x anyway.
Oh, okay.
Right? Right? Because if I plug in a equals 1, I still would have b and x in play. I'd still have to plug in something anyway. I might as well still just plug in something that gives me less things to worry about. So that's the partial fraction for that.
Sorry, one more question.
Yes.
What happens if you don't get a 1, then how would you do it? Like, how would you integrate it if you don't get a 1?
Don't worry about integration for now. Just worry about breaking this up.
Oh,
We'll
okay.
get to the integration. Don't rush it. Just think of, make sure you understand this process. Method 2 for finding the things. Step 1 is the same. Multiply both sides by the denominator on the left. The second thing you're going to do in this case is multiply out group like powers, meaning combine like terms, and equate coefficients. So let's say I had that same thing again. Just This is going to be x minus 3, a on top of that, b on top of the x minus 2. I would multiply through by this denominator. Now what I would do, instead of plugging in convenient values, I'm just going to multiply out. This is ax minus 2a plus bx minus 3b. I'm going to group like terms, group like powers. So the x's over here, I have a plus b x's. And as for the constants, the 0th powers, I have minus 2a minus 3b. And now what happens is that this is an equation, so the number of things on each side have to be the same. On this side, you'll notice I have 0 x's, and the constant is 1. What that means is, if I have 0 x's over here, I have to have 0 x's over there. So my a plus b must be 0. It also stands to reason that minus 2a minus 3b must be equal to 1. So, step 3, set up and solve the simultaneous equations. You'll get a plus b equals 0, and you get minus 2a minus 3b equals 1. And, I mean, you'll know how to do it. Say a equals minus b. Plug that in the second one. You get 2b minus 3b equals 1. You get b equals minus 1. Substitute back that here. You get a equals plus 1. Again, you obtain So, you're going to be you need to be really good at dealing with rational things. So here's the exercise that I will say do until Friday. Write down some small fractions of just make up whatever, like whatever comes to mind. 1 over x plus 1 minus 1 over x squared plus 1, right? Add them yourself, and then use partial fractions to break it back up and to see if you get back your original answer. Actually, just make up something and try to build it up and then break it back down, because we're going to need to be good at dealing with rational functions for this section. That will be good practice. Yeah, tomorrow we'll do a little bit more practice here, but then we'll actually get into integration. Not tomorrow, Friday. For now, we'll stop there. Yes.
So what happens if when we gave it to that, and we said x minus 3, x minus 2, that cannot be factored like that.
Well, if it cannot be factored, let's say you have something that can't be factored, then you don't do the factor.
So it has to be factored.
Yeah, you have to be able to factor the denominator.
Also,
Thank you.
All right, I see you.